Maybe did a bunch of those All right, here we go. Static electricity. Um, we're gonna look at ways of charging. So by the end of this lesson, you'll be able to describe what happens at atomic levels to conductors and insulators when next to a charged object, and describe three different ways an object contains electrical charge. Here we go. Quick chemistry review, not to bore you. Electrons, protons, and neutrons. Electrons are on the outside, protons and neutrons are on the inside. Which of these are responsible for doing chemical reactions? What's the players that are important? Electrons. Good job. So we're going to focus on those. So if an object is positively charged, it has more protons than electrons. If it's negatively charged, it has more electrons than protons. If it's neutrally charged, bless you, it has no protons or electrons at all, right? Just kidding. It's the same amount. Even Steven. Good? Okay. When two objects that are charged with the same charge are brought near, what happens? They attract. They repel. Oppositely charged. Oppositely charges attract. Thank you for giving me some little. Okay, conservation of charge. It's this idea that when you do a chemical reaction, you don't eat or birth electrons. They're still all there. You get at that. Like charge isn't created or destroyed. It's all just there, just transferred in some different arrangement. Good? Electrons are the thing we're going to focus on. Electrons are the only thing that transfers. Protons are stuck in the nucleus. Good? So electrons are the players that we're focused on. Yes? Good? Okay, that's your chemistry review. Not too bad, yeah? Okay. So, give me some examples of electrical conductors. Materials, what do you got?
Copper.
Copper. What? So this one's easy. This is like ink, think. Gold. Silver. Okay. Metals. Any type of metal. Conductor. Yes? Okay. What does conductor do? This allows electrons to transfer readily or easily. Allows electrons to transfer easily. Okay. Conductor. Microscopically, how is that possible? In chemistry class, did you guys ever express metals? So the transition metals, in chemistry, you got your twin towers on the periodic table, and then the valley in the middle. Okay, that's your transition metals. Okay, when those bond together, they have what in chemistry they call a sea of electrons. It's kind of like a hippie community. It's like, hey, dude, can I borrow your electron? Yeah, sure, man, that's cool. My electron's your electron. That's sweet, man. Yeah. Okay, just kind of so long as all electrons are there, that's all they care about. Good? Okay. Give me some examples of an insulator. Insulators. Materials. What do you got? Lots of them. Rubber. Wood. Goodness, kids. Plastic. Glass. Ceramics. Okay, are all insulators. Okay, so they prevent electrons from easily transferred. So microscopically, these are possessive of their electrons. Kind of like reminds me of American Suburbia. Okay, dude, can I borrow your lawnmower? No. Yeah, but you're not using it. Yeah, but I will on like Saturday. Yeah, but it's like Wednesday. Like, go buy your own lawnmower. Like, you're not using it. Buy your own. Everybody's like in their own little white picket fence. Like, hey, can I borrow an electron? No. Hey, you want one of these? No. Get your own. I got my happy gate. Get out of here. Get with that? Yeah. All right. So, So, when molecules bond together in a material, they have a crystal lattice. This is going to be my rendition of a crystal lattice. This represents a neutral object. Protons are in the nucleus, electrons are on the outside. It's like it's a 4-to-1 ratio. Yeah, just go with it. It's neutral, all right? Good? Okay. So one distinction between chemistry and physics is chemistry focused on individual atoms or molecules. In physics, we look at macro-sized objects. So this would be like a neutral conductor, and we'll say that's a stapler. It's like you can hold it in your hand, you can see with your eyes. There's like bazillions of electrons and protons on here. It's neutral. Okay. This negatively charged thing is not an electron. It's like a negatively charged bowling ball. Right with that? So what do you think happens when you bring a negatively charged bowling ball next to a neutral, near a neutral stapler? There are your options. Protons run towards it, electrons run away. Protons stay put, electrons run away. Electrons run towards, protons run away. Electrons run towards, protons stay put. Have a conversation. Okay. Is everybody good with C and D are not an option? Okay. Opposites attract, likes repel. Okay. Correct answer is B. Protons stay put in the nucleus. Only electrons can move. Good with that? So only electrons move. All right. So when something is polarized, so you have, this would be an example of an object being polarized. Overall, it's neutral, but this side is partially positive, this side is partially negative. You guys use those symbols in chemistry? The polarized, like remember H2O, like Mickey Mouse, the polar molecule is partially positive, partially negative. Yes, no, maybe so. Overall, it's neutral, but one side favors a charge, the other is the opposite. It's polarized. Let me throw some words on the screen there. When one side of the object is partially charged, opposite side is charged. On this side, and I'm using opposites twice, whatever. All right. But overall, it is neutral. That shoot from the head there. Okay, and one side of the object is partially charged one way, and the opposite side is charged the opposite. But overall, it's neutrally charged. Good. How are we with that? So, what do you think happens when you do the same experiment but with an insulator? You bring a negatively charged bowling ball next to a neutral insulator. Here are your options. No response. Electrons run to the far side of the molecule throughout the entire object. The electrons run to the far side of the object. The electrons run to the far side of the molecule, but that effect diminishes as you get away from the object. One of the cool things about this semester is you're not coming in with a bunch of misconceptions. You're just like, I don't know. Here's my guess. And it's like, here's the answer. And you're like, oh, okay. I don't have to break bad physics that you've already established. Correct answer is D, dangerous dinosaurs. So they run to the backside of, so in like American suburbia, electrons are like plastered against the picket fence, like oh yeah, like you can't leave, like ah. And that effect diminishes as you go away from it. It's like, oh, your house caught on fire, that sucks, glad it's not me. See that? Okay. Interactions of charged objects. You bring a neutral object near a positively charged object. What will happen? In chemistry, we would say it does nothing, it's neutral. Okay, but in physics, because it's a macro-sized object, there is polarization that can occur. And so there will be attraction. Okay, because here, this is an extreme case. The positives are closer to this negatively charged, so the force of attraction is greater than the force of repulsion because these are further away, and so it's going to attract because it polarizes. Okay with that? Okay, so
know how you take a balloon, rub it on your head and stick it to a wall? Okay. The wall is neutral. When you bring the charged balloon next to it, the electrons are pushed to the far side of the molecule. And there's still attraction. The wall is neutral. Get that? Give that. Have a conversation. Correct answer is. What do you say? Correct answer is F. Okay? You guys know what static cling is, right? You guys are doing your own laundry at this point, right? If you aren't, you need to learn. It's a good life skill. Okay. All right. There are three different ways something attains a charge. The first way is charging by friction. The scientific word for that is triboelectric. Don't worry about that. I'm never going to ask you that. But this is the type of charging that you are probably most familiar with. So this is anytime you've like shocked something or something has shocked you, it's probably because of charging by friction. Okay. So this occurs when two insulators related to materials are rubbed together. And one material likes electrons more than the other. Two insulative materials are rubbed together, and one material likes electrons more than the other. Charging by friction. Give me examples from your life where you've been shocked and you're like recounting like what caused that. You're like, oh, and these two things are rubbed. Give me examples when you've been shocked.
When I was a kid on the slide.
Yes.
On the playground.
Going down a slide, a plastic slide on a playground. Ow, ow, ow. A trampoline, yes. Oh. Yes, carpet. Rocks on a carpet, shoes on a carpet. Getting in and out of a car. You're rubbing your butt across the seat, and then you go to touch your car. Yes. And it happens all the time in the wintertime. Pay attention. Next time you get shocked, you're like, why did I don't know. Okay? So, what determines which material becomes positively, which becomes negatively charged? You do not need to memorize this. But these type of materials tend to give away electrons. These type of materials tend to want electrons. It's a attribute called electron affinity or electronegativity. Okay, these tend to be more organic, natural materials. These tend to be more synthetic, man-made materials. It's not in all ways, but polymers. Good with that? Okay. So, charging by friction. Let's say you charged a piece of metal by friction. How would the electrons, say you charge it negatively, how would the electrons distribute themselves on that conductor, on that sphere? Okay. Does everybody see I'm just going to tell you because you're just guessing. Okay. But you see the options. Okay. Correct answer is C. So here's what I want you to write down. A conductor, a charged conductor, the charge will always reside on the outside surface. Okay. The charge on a conductor will always reside on the outer surface. That's the fact of what I want you to walk away from. And on a conductor, the charge will always reside on the outer surface, not in the middle. Good? Okay. So what would happen if we charged an insulator by friction? And same choices. Correct answer is E. Okay, only where it's rubbed. Okay. These guys in here are like, we got a lot of electrons. And all the other guys are like, sorry about your luck, buddy. You're stuck. Good? All right, so that was charging by friction. Charging by conduction, okay? This conduction, think of like touching, physical contact, okay? So, if we take a neutral conductor, and then we bring a negatively charged object, negatively charged bowling ball near it, it polarizes. Okay? When you touch something, this allows electrons to transfer. There's a physical connection. Electrons can transfer. Okay? So, if you were an electron on this negatively charged bowling ball, where do you think you would rather be? In the bowling ball or over here where there's a lot of exposed protons? Think that's not too hard of a choice, right? You're like, it's really crowded over here. Like, look at all those woo! Well, so when they touch, electrons are able to transfer over. Making this now what? Charged. Good. I heard a lot of thoughts. Negatively charged. Good with that? Okay, we just gained electrons. Charging by conduction, you touched. Okay. All right, so let's say we have a neutral conductor and we're bringing a positively charged object near it, and we're touching it to the neutral conductor. What happens? Thumbs up when you got something. Tell your neighbor what you think.
Yeah.
Yeah, because the proton's breaking.
Correct answer is, what do you say? Correct answer is C. Okay. So, protons stay put. Electrons are like, woo, look at all those protons. Polarizes. When it touches, that allows electrons to transfer, and they jump off. So as only electrons move, electrons jump off the conductor onto the positively charged object, making this now positively charged, electron deficient. Good? Yep. All right, before we, so that's charging by conduction. So we got friction and conduction. Before we talk about the third way, we need to have this conversation about ground. So, have you ever heard this idea of electrical ground? Like the ground wire, something got grounded, not a punishment, but like electrically, okay? In your house, that third prong is the ground wire, and it is at somewhere connected to the dirt, usually through your pipes, your water pipes, okay? So this is where we get this idea of ground, like it's actually going to the earth. So it's this idea that ground is anything that is huge and neutral. And even if you dump charge into it, it's still going to be neutral. It's like taking a 5-gallon bucket into the ocean and like dumping that into the ocean, like, just raise the sea level. Like, no, we've done it. Okay, so like, it doesn't really affect it. Okay, so in the lab tomorrow, you are going to be huge and neutral compared to the objects we were working with. So you will be ground compared to the things. Okay? So, some examples we see in life is like if you're working with electronics, you don't want to accidentally shock something and destroy some circuitry, so you wear the grounding strip, prevent that. When trucks unload stuff, sometimes you get friction going on here, A lot of times you'll see this around, so in the farming community, when you go to the grain elevator and you deposit your corn or soybeans, the dust from the corn and soybeans is combustible. And so there's a lot of friction that happens as you're unloading that. So you have the ground wire to prevent some static discharge. That. Good? All right. Charging by induction. This is a process. Okay. So step one is we bring a charged object near a neutral object, and the neutral object responds. So think about what would happen inside this neutral object. Polarizes, electrons are like, ooh, look at all the protons. Good with that? So it polarizes. So step one, charged object causes neutral object to polarize. Step two, we connect the opposite side to ground. So ground is something huge and neutral. So here's the killer. Electrons, they're not satisfied. They're always want a better ratio. They're not satisfied with a 1-to-1 ratio of protons to electrons. If they can have like a 2-to-1, they're like, yeah. So where would electrons rather be? In a 1-to-1 ratio or with all these exposed protons? If you're thinking opportunistic, you're like, look at, woo! So electrons come up here, like, hey, how you doing? That makes sense? Okay. So that was step two, connected to ground. Step three, we remove that ground, the ability to transfer. Okay, and then we take away the charged object. At which point in time, these guys are like, oh man, I guess we'll go back home. And they come in like, what? Whoa, who invited, what is that? And so now the overall charge is what? Negative charge. We just charged that object by induction. Okay? So the process is you bring a charged object near to polarize it, ground the opposite side, allow electrons to transfer, take away that grounding, the way to transfer it, and then you take that away. Like, charging by induction. Okay? So, neighbor, what do you think?
Yes, one. It's very
Correct answer is. What do you say? Correct answer is now C. Okay, we got positives. Electrons in here, like, wait a minute, sorry. Okay, got negatives in here, the electrons in here, like, run away. So when you connect it to ground, sometimes you'll see this in wiring diagrams, this arrow. That's ground. If you were an electron, where would you rather be? In this, being scared by that guy, or in this sea of electrons where there's like 1-to-1 ratio? Man, I'm out of here. So they jump ship. Believe in this now. Positively charged. With that, charging by induction. Okay. So friction, conduction, touching, induction, taunting, grounding. Good? Okay. Tomorrow we're going to start a lab where the objects we're going to be focusing on are these packaging peanuts that have been painted with a metallic paint. We're going to use these because they're lightweight. If we had a metal ball, it would be a conductor, but they're really heavy and they don't respond as quickly. These guys, because they're lightweight, still act like a conductor because of the metallic paint. Okay? So, this is a rod made out of a rubber. When wrapped with rabbit fur, this was Thumper. This becomes negatively charged. Okay? In the lab, this will always be negatively charged. It will never become neutral or positive. It will always become negatively charged. It might be more or less negatively charged, but it will always be negative. Okay? This clear strip, when rubbed with paper, will always be positively charged. Never neutral or negative. Always positive. Might be more or less positively charged throughout the lab, but never neutral or negative. Okay, always positive. Good with that? Okay, so I'm ready to experiment tomorrow. You got a pre-quiz due tomorrow.